Hi, this is the 19th part of a series of videos about parametric curves. We've been focused on using these curves in a physics kind of way to model motion and developing calculus tools from an intuitive physical graphical perspective to help us understand these curves in recent videos. We haven't delved into the details of why the calculus works. Hopefully we can do some of that later. We've been trusting this program called Mathematica to take derivatives and calculate integrals for us that will do those calculations and tell us about the curves. In the last couple videos I introduced you to the idea of a vector, and in particular something called a position vector. What is a vector and what is it good for? Well, when you draw vectors, and oftentimes you do draw them, you typically draw them as arrows. What are some distinguishing properties of arrows that distinguish one arrow from another? One property is the length of the arrow. A second property is the direction that it points in. Say it's in the plane, it might point to the northwest or to the south or east. And a third property is where is the arrow located? Where do you start the arrow? Where is its base? If you change the base, that's called translating the vector. And what we'll see is that as far as the algebra of vectors goes, translating vectors doesn't make a difference. However, translating vectors is still important because it will affect how we interpret the meaning of the vector for physical situations. In the last video I also talked about notation for vectors. I'll remind you of that and I'll also show you some alternative notations. I'll talk about scaling vectors, making them longer or shorter, and hopefully if we have time in this video we'll get to velocity vectors, which is a related idea that can help us analyze motion. So going back to the animation at the end of the last video, here it was. Here we have a motion. The dot is the object that is moving, maybe a person walking along the line. That red line is the parametric curve drawn out. It's a geometric realization of that. It's the path of motion. And the black arrow pointing at the dot, going from the origin to the dot, is called the position vector for the motion. It makes good sense to start this position vector at the origin and have its tip be at the location of the person as they move. That makes good physical sense. So we keep a position vector to start at the origin and point at the location of the person as they move. Where is that point? Based on the function notation I've been using, it's this point right here. Go back and look at some old videos to see the meaning of these functions, f, g, h, and c. Because of this natural place to put a position vector, it makes sense to associate the position vector with the point. What does that mean? It means, first of all, well, it's not a point. The arrow is not a point, so notationally we don't write the exact same thing. I don't use point notation here. I don't put parentheses around here. But it is associated with a point. This is reminiscent of a point. This looks a lot like this does over here. We also use boldface type when we denote a vector to emphasize that it is a vector, at least when you use typewritten work in books. Oftentimes, by hand, teachers, scientists will use a half arrow above the letter for the vector to indicate that it's a vector when they write it out by hand. Not everybody does that. Some people write a full arrow, some people put a line under the vector. Okay, I like using a half arrow because it's just a very quick thing to do that emphasizes that it's a vector. There are other alternative notations for vectors. When you're using vectors in the context of something called linear algebra, you often write vectors as a column like this. You're still emphasizing that you've got two numbers, two quantities that are representing the vector in this way, but it makes more sense in terms of what's called matrix vector multiplication to represent it this way. Another representation you'll see sometimes used is instead of these brackets that look like less than signs and greater than signs, you'll see actual square brackets around this. That's another notation. And finally, yet another notation is some people don't worry about the fact that the vector is not technically a point and they go ahead and make it look like a point. But I will use this notation here, which is the same notation that John Rogoski uses in the book that I'm following here about multivariable calculus, to emphasize that this vector is an arrow rather than a point, but it is related to a point. All right. I want to talk about those other issues, translation, scaling, and scaling in the context of something called a velocity vector. And what I want to do is I want to go back up to my, let's see, my paraplot here, and I want to add in something. I'm going to add in another vector, but it's not going to be a vector that is stationary initially. Excuse me, it's not going to be a vector that moves initially. It's going to be stationary. I think I will make it blue to distinguish it here. I am initially going to start it at the origin, but I'm going to go to a different point. I'm going to go to a fixed point here, and the point I'm going to pick is the point -3, 4. Seems like I pulled that out of the air, but I did do that for a particular reason. Also down here, I'm going to go back to the constant speed motion. I'm going to make the h of t be just a t. Okay, so now I've added this blue arrow, this fixed blue arrow that's not going to change as the animation goes by. Why did I pick -3, 4? I hope you can tell by looking at this here. You should notice that -3, 4, the vector that starts at the origin and ends at the point -3, 4, that vector is parallel to the motion here. I picked it for another reason. It's also just as long as the line segment that you see here once the motion is completed. In the Pythagorean theorem implies that the length of this line segment is 5, therefore the length of this arrow is also 5. They're parallel and they point in the same direction. So in a sense, because of that, and because, well, remember this is a constant speed over 1 second, and if the units of distance are measured in meters, you should recall, or you should be able to recalculate that the speed here is 5 meters per second. So I've made an arrow in blue here that points in the direction of motion and also has a length equal to the speed. You got that? This blue arrow in this constant speed motion case points in the direction of the motion and has length equal to the speed of 5 meters per second. It makes sense to call this thing a velocity vector. Now, if you've never heard the word velocity before, you might wonder where it comes from. People sometimes think of velocity and speed as being synonymous. They're not. Speed is a rate of change of how fast you're traveling over a certain distance. Velocity takes direction into account, whereas speed doesn't. But I also want to give myself freedom to perhaps move this vector. And in fact, if you think about it, it would make good sense to put the velocity vector not at the origin, but instead to be at the point where the person is located. Because then the fact that these are parallel would be highlighted even more. And later when we talk about curve motion, probably the next video, we'll see that the velocity vector will be tangent to the curve. All right, we talked about tangent lines before. Tangent vectors are a related idea. All right, so where should we put the vector? We should go back up here. I want to now base the vector at not at the origin, but instead at the point where the person is located. And so I'm typing in a C of h of b. Will this work? Let's see if this works when I enter this. Guess what? It doesn't work. That's because I'm keeping the tip of the vector at the point -3, 4. How can I make it work? Well, it turns out if you go back up here and take this -3, 4 and for a mysterious reason somehow add h of b to it, I'm going to put a plus sign in here, C of h of b, all of a sudden that's something that works. Now that might be kind of mysterious. How can I add points like that? The technical math answer is that I'm not really adding points, I'm adding vectors. But that might be confusing. Am I really doing that? Well, I'll talk about that in future videos, probably the next one in fact. But here we have the basic idea. This vector is pointing in the direction of the motion, the blue vector, and its length is equal to the speed, the constant speed in this example. If we have varying speed, some other h of t, like square root of t, probably we would want the length of the blue vector to vary as well, and always have a length equal to the speed We'll get to that in the next video, hopefully, as well as curve motion, though I'm not quite sure if I'll get to that in the next video.